Hello, George Romanic here. Mean free path is average distance an atom will travel before colliding with another atom in an ideal gas, such as air, in your room or my room. We will use the principles of kinetic theory of gases, Maxwell-Boltzmann distribution, and all this beautiful stuff to derive this quantity that has very important implication on how we perceive air around us and how we can use Navier-Stokes equations to describe motion of air. Let's start. Let us first look into this conceptually. Here we have, let's say, atom 1, and this atom has this diameter d. The atom is moving in this direction and let's say it has velocity v1. This is the volume that the atom v1 will sweep over some time delta t as it is moving in this direction. And I say volume because remember this is a sphere. Now if we have, let's assume, some atom, let's say here, atom 2 that is standing still, or let's say moving even better, with some velocity v2, like so, clearly these two will pass next to each other and there will be no collision. The collision will occur only if this atom 2 is located here at worst or somewhere inside of this volume that atom 1 will sweep. So this is the first instance when there will be collision between atom 1 and atom 2 because they will just touch over here. Of course, the same holds if I go here, if I have some atom, let's say some atom 3, I don't know, here moving in this direction, then there will be collision between these. If atom 3 was more, so to speak, north, there will be no collision. And of course you might say, but what happens from some other directions? Well, I can always look into this situation from some other direction, okay? So in other words, if we now observe this whole thing from this direction, you will see that there is this atom, which I will call reference atom, my atom 1, that has this diameter d, and it will only collide with other atoms that are, so to speak, touching it or are more in the line of the motion of this atom. So the atom 2 could be here, could be here, could be, I don't know, here. All of these circles should be same size because these are all identical atoms, at least in this theory that I'm developing here. So you can see that we can identify this sphere of collision, so to speak, that is like that. And because diameter of this atom is also d, as well as diameter of this atom is also d, you can see that effective area of collision, so this will be, let's call it A effective collision area, will have diameter that is 2d, because you get 1d from our reference particle, you get half a d from this one and half a d from this side. So the effective diameter of the effective collision area is simply 2 times d, which means that the effective collision area is simply pi times d squared. Okay, we are making some progress. At least we found this effective area of collision. Now we have to combine this figure together with the concept of this atom moving in certain direction. So let's do that. Let's say here I have that atom of diameter d, my reference atom, which I called atom 1, and it is moving in this direction, and around that atom, as I just indicated, there is this effective collision area. That means it will sweep this volume like so. This over here is distance that atom 1 will cover in some time delta t. First, let's discuss what is the volume that will be swept in this time delta t. And by volume, I mean effective collision volume. So V effective, that's volume, not velocity, is equal, of course, this effective area times this distance in time delta t, let's call this distance delta s, times this distance delta s. And now this is where we have to be subtle, because it is tempting, it is very tempting to say that this distance, I will write answer that is wrong. It is tempting to say that this distance delta s is mean speed of atoms in a gas, because that's the mean speed of any atom, including my reference atom 1, times time delta t. It is tempting to say it's this. But it is not that. It is not that, because if I have atoms and these dots represent center of atom over here, so I don't have too many spheres. These are centers of these atoms. If I have other atoms in this effective volume, they are also moving. If they were standing still, this would be correct answer. But this is incorrect answer, because there is a relative speed between reference atom 1 and all other atoms in my effective volume. And from my video on relative speeds, you know that mean relative speed is equal square root of 2 mean speed. I went into great lengths in my video on relative speeds to demonstrate this. So that means that this distance is really square root of 2 times mean speed times time delta t. In many videos, they tell you that in principle distance is this, but if you carry out more subtle analysis, you'll get factor square root of 2. Now you understand how you get this factor. Okay, now we are in the position to calculate this effective volume, and that will be A effective times square root of 2 times mean speed times delta t. So you will get square root of 2 times pi times d squared. So just for you that forgot, it comes from here, pi d squared is effective area, times mean speed times delta t. So what we found now is the effective volume, this. The next step is to quantify how many particles is in this effective volume. You see here I pointed out 4. But the question is how many? If there is none, then all this discussion is for nothing. There will be no collision. Let's see how many. Let's take a container with a gas. That container could be your lungs, could be your room, your basement, box for your shoes, whatever. This container has a lot of atoms. And I will say that N is total number of atoms in this container. Volume of this container I will call V box. Now, as I said, this box could be your shoe box or your lungs, and I'm not interested in these. I'm interested in number of atoms per unit volume. And of course, that would be number of atoms in this box per volume of this box. Therefore, number of atoms in any part of this box, and that could be this effective volume, is equal this n times volume of this subdomain. That should be clear. So n times V effective is number of atoms in effective volume. Now we have to deliver the final blow, and that is the following. I know how many atoms is over here, so I can define a path called mean free path that is length of the path of this reference particle in time delta t, of course, divided by the number of collisions in that time delta t. So what I just said is I will define a length called lambda that is equal length of path of our reference particle divided by the number of collisions in delta t, and of course length of this path in time delta t. Well, what would that be now in terms of these quantities? That lambda would be length of path of our reference particle, that is mean speed of my particle times delta t, divided number of collisions in delta t. Well, it will collide with all these atoms that are in this effective volume. And I have this many atoms in my effective volume. And that is square root of 2 times pi times d squared times mean speed times delta t and times this n. Notice that this and this cancels, time and time cancels, and I will get that lambda is equal 1 divided by square root of 2 pi d squared times n. And this quantity is called mean free path. That is the average distance between two collisions in a gas. Now this is very good result, but we can make it even better because this n is difficult to find. So we can replace n using equation of state for an ideal gas. We know for this box over here that pressure in the box times volume of our box is equal number of atoms in this whole box times Boltzmann constant times absolute temperature. So if I divide this equation by V box, notice that I will get that pressure is equal n divided by V box is small n times K times T. And now instead of n, I can plug in here pressure, Boltzmann constant and T, and I will get that result is that lambda is equal K times T divided by square root of 2 pi d squared and times pressure. And this is astonishing result because again we found a characteristic variable of our gas, and that is the mean free path. We can see if temperature is high, then the mean free path is high, larger. If pressure is large, mean free path is smaller. And that makes sense because you compress gas, and that means there is smaller distance on average that the atoms will travel before colliding with other atoms. And of course, when you increase temperature, jiggling increases. So on average, there will be larger distance that atoms traverse before they collide with adjacent atom. Here is a calculation that I performed for typical gases in your room, namely gases that constitute air, and I added radon, you can see that mean free path is order of magnitude 10 to power 7 or 10 to power 8, depending on the gas, and I calculated this for room pressure of 1000 millibar and room temperature of 23 degrees Celsius. 10 to power negative 7, or of course 10 to power negative 8, are extremely small numbers, and I wanted to express this in terms of millimeters as well. Millimeter is so small. Here I have a ruler, and this is 1 centimeter. 1 millimeter is really small distance, and yet we have that mean free path of, for example, nitrogen, that is 78% of your air, is 0.1234 zeros and then number. That is very small distance indeed. Also notice that mean free path is actually much larger than diameter of our atoms. Diameter is here given in angstroms, and angstrom is 10 to power negative 10 meters. So you can see that mean free path is 1,000 to 100 to 1,000 times or so larger than the diameter of the atoms. And this is very important, because we said the main assumption of kinetic theory of gases is that on average particles are much further away than their size. And you can see that here this assumption is satisfied. That was the first assumption that I introduced in our series on kinetic theory of gases. So yes, mean free path, despite being very small, is still much larger than the diameter of these atoms. Lastly, I would like to say that this video nicely connects to the very first video that I published on this paper, on this channel, and that is video on Knudsen number. Knudsen number, you will remember, was defined as mean free path, lambda, divided by some characteristic length, L. And this number is used to quantify whether or not we are in continuum flow or kinetic theory of gases. If Knudsen number is smaller than 0.01, then we can use the assumption of continuum, and we can use Navier-Stokes equations that I derived. If, on the other hand, this is not satisfied, then Navier-Stokes equations cannot be used, and you have to use kinetic theory of gases. So you can see that now explicitly deriving the value of mean free path, the Knudsen number Kn, discovered by Danish physicist Martin Knudsen, is Kt divided by square root of 2 pi d squared times pressure and times characteristic length of this container that you are maybe interested in. In my video on Knudsen number, we calculated this quantity for lungs and nose and so on, and we saw that in all these cases this number is extraordinarily small, which means we can use Navier-Stokes equations. And that's not any surprise. We use Navier-Stokes equations every day to describe motion of air. We don't use kinetic theory of gases, because you understand why. Because characteristic length of these distances is much larger than the mean free path. Mean free path has very small value. Order of magnitude 10 to power negative 7 meters or even 10 to power negative 8 meters. Yet, that value is very important when coupled with typical distances that we encounter in everyday life. Because through the concept of Knudsen number, we can see that we can rely on the physics of continuum to describe motion of air at everyday scales around us. That is only because mean free path has these typical values at environmental conditions, namely temperature and pressure of gas that we encounter around us. Yet, I think it is very important to know that when we use Navier-Stokes equations, the fundamental background behind that lies in kinetic theory of gases. Of course, one could go deeper and go into quantum physics and explore matter at even more fundamental level, and perhaps we will do it in one of the next playlists on this channel. But for now, we could say that kinetic theory of gases is the fundamental theory that describes interaction between particles in an ideal gas, such as air in the atmosphere. Until next video, goodbye.